Okay, this is the last video on the study guide. So, I think I was up to number 13. Um, what does the amplitude of any mechanical wave indicate about the wave? What would a sound wave with a large amplitude sound like? So, amplitude, remember, let's see if I just draw a quick waveform here. Amplitude is this maximum displacement from equilibrium. So if this graph went up to 2 meters, say, my amplitude would be 2 meters. And amplitude is connected to energy. If a wave has a larger amplitude, then it's carrying more energy. So a sound wave with a large amplitude is a sound wave with more energy, and that means it's going to be louder. That is connected to loudness. So remember, we have pitch, which is connected to frequency, and then amplitude or loudness is connected to amplitude or energy. Okay. Here are two waveforms that we're comparing. They're moving through the same medium. Okay, so the same material. All right, so amplitude, we just talked about that. We can look at this distance from here to here. That looks like 6 meters for the first wave and 6 meters also for the second wave. Okay. If I compare their frequency, I don't know that I have information here to help me get a value for frequency, but I can see that this wave is going to have, because these are the same scale here at the bottom, this wave has got less cycles per time period than this wave does. So that means this wave is going to have a lower frequency, wave A, than wave B is. And you can see that by there's a lot more cycles here than there are for this wave. And then because these two are inverse, okay, and then I can also see this from the picture, the wavelength of wave A is longer. Like one waveform has a longer length. And again, I don't really have a way to measure that on here, but I can just see it looking at the graphs because these are the same scales. One wavelength has a much longer length for A than B. B is a lot shorter. If you compare this length to this length, okay? So if you have a lower frequency wave, it's going to have a longer wavelength because those two are inverse. And then the opposite of that, if you've got a high frequency wave, it's going to have a shorter wavelength. We'll see those two things again a lot when we get into electromagnetic waves. The speed of these waves is the same because they're in the same medium. They're in the same material. So their wave speed is going to be the same. They just have a different combination of frequency and wavelength. Remember, speed equals frequency times wavelength. And then pitch. So thinking about pitch, which I just said connects to frequency. If this wave has got a lower frequency, it's going to have a lower pitch if this was a sound wave. And then this wave is got a higher frequency, so it's going to have a higher pitch. Okay. All right. And then I got a little bit at the bottom here about wave interference. Okay, so there's sometimes wave pulses will combine with each other, and they combine in different ways. So we want to talk about that for a few minutes. So let's say these two wave pulses are moving towards each other. They combine and their amplitudes basically add up. Okay, they combine to form a larger pulse. See how this pulse is larger than these two. When two wave pulses interfere such that their pulses combine into a larger amplitude, that's called constructive interference. Okay, and maybe that kind of makes sense based on the description, but your two waves, your amplitudes are adding up when that happens. And you're getting one combined wave that's got a larger energy because your two amplitudes are adding up. The opposite of that is when, and this isn't a very good graphic here, two waves combine such that their pulses cancel each other out. Really, this would look like one that looks like that and one that looks like that. Okay. Their peaks are like opposite of each other. They combine, and you can see here that instead of the amplitudes adding, it's almost like one subtracting from another. And this is called destructive interference. So sometimes when waves are bouncing back and forth off of something and they combine with each other, sometimes they'll make a larger amplitude wave where their energies combine. That's called constructive interference. Sometimes they'll cancel each other out. And that's called destructive. And then the standing wave, we looked at that last week when we did our air columns lab. This is where waves overlap with each other inside a container, like we talked about how they would overlap inside those little column type palm pipes that we used. They overlap such that they look like they're standing still. That's why they're called standing waves. And standing waves have two parts. They have a node. This is the node. So this is where it cancels itself out. This is like a destructive interference. That's an area of zero amplitude or low energy. And then antinodes, the opposite. This is where my two amplitudes have combined as a max, and that gives me a high energy. So nodes are the little dots here where they cancel each other out. Antinodes is where they are like adding up at a maximum. So, all right, that is everything on waves and sound.